on his mini course on large deviations on random graphs.
All right, so yeah, thanks. Let me share my screen. So. Okay. All right, so yeah, we'll carry over from where we left off. I'll briefly sort of recall what we did yesterday, and then I also sort of there will be lecture notes available online about everything that I'm going to talk about, and actually more. And also the things that I'm writing up during the lecture will also be posted after every lecture. So I think you should expect the material from yesterday to be online very soon. Okay, so just to recap, so yesterday we saw how for p not too small, the property of this tail events where th is number of copies of H inside G. You can also think of it as homomorphism counts because for P not too small, those things are pretty much the same. This is roughly exponential of something, which I was calling, I guess, H and P delta plus maybe some correction. And this was an optimization problem. This was a solution to an optimization problem, which was you look at the best possible reweighting. So Q is a weighted graph. You look at the relative entropy of the entries of Qn with respect to P, and Q is such that is actually typically pretty large. Okay, so this is where we stopped yesterday. So roughly for P not too small, the optimal strategy is to have a inhomogeneous random graph, which makes the atypical event that you want to attain typical. And the cost is the relative entropy. Just to be concrete, this is Q is a weighted graph. And just to be concrete, this is this is a symmetric matrix. So, but let's just do I not equal to J, relative entropy of IP of Qij. So this is something that we defined yesterday, which was the relative entropy of a Bernoulli random variable with mean Qij with respect to Bernoulli random variable of mean P. And then you sum over all things, but like the degree of freedom is actually not the full matrix, but only half of it because it's symmetric. And so basically, every term actually gets counted twice. So you essentially actually, this is the cost. Now, at this point, there are a couple of things of interest. Is what is so what is the solution? Now, for P, let's for the moment just stick with P. That's it. By the way, I should actually sort of, yeah, I forgot to sort of open my chat box. Actually, let's. Okay, sorry. Okay. So for the moment, let's just maybe briefly spend some time when P is, let's say, fixed. Although yesterday we did talk about P going to 0 with n very slowly maybe, but still P was allowed to be going to 0. But let's for the moment assume that P is fixed. And then actually this quantity, which is an n in it, is actually related to a continuum problem. So there is a graphon where, let's say, and so this is going to be exactly the same as this, but instead of a weighted graph of size n, I'll look at a graphon. So again, it's the same thing. Now this is going to be a graphon, and I essentially minimize over IP of Q a graphon, such that something pretty similar to this holds. Right, so now I want to sort of take a continuous function on 0, 1 square. So yeah, I guess I don't have to recall everything from yesterday's lecture, but we sort of briefly talked about graphons, which were the continuous version of graphs, where graphs actually naturally embed as graphons. And these are just 0, 1 valued functions, which is symmetric on 0, 1 square. And so IP of Q is now just, this sum is actually just going to be replaced by an integral. So it's literally half integral IP of QXY. Okay, so this is a natural way that the discrete problem transforms into a continuous problem. It's actually sometimes simpler to work with the continuous problem, and it's actually not very hard to go back and forth between the two. Okay, so instead of asking this question, I'll sort of ask the same question about phi HP delta. Okay, so natural question is when and also let's say the argmax. So this is an infimum. Everything is actually compact, but you can ask about what is the graphon that minimizes this. When is phi HP delta attained at a constant function, which is the same as roughly saying the large deviation event makes GNP, which was the original measure that I started with, behave like GNR for some R. Like in this case, we are looking at upper tail events, but you can also look at lower tail events. But for the moment, just let's just sort of focus on upper tail events. So we had sort of asked this question in the past, like when do you expect an Edersonian graph with density P under this conditioning to behave like an Edersonian graph, homogeneous, where everything sort of gets simultaneously raised to density R. Now this is so you have to sort of solve this. So this is a convex function in Q. Relative entropy is a convex function in Q. But the set on which you're minimizing it is not convex. So it's actually not super clear how to actually solve this optimization problem. Now it turns out, okay, so Lubetsky-Zhao using a generalized form of Hilbert's inequality found the above region exactly when H is regular. So H is the graph that we're embedding. So H is a graph whose number of copies we're interested in. We want it to be larger than its typical value by a multiplicative factor. And And we want to understand the graphon, which has that property typically and has the smallest entropy cost with respect to the original measure, which is constant p. Now, like I said, so this is sort of a non-trivial problem, but it turns out there's a sort of nice application of Hilbert's inequality, which only works for regular graphs. And I will tell you roughly what the solution is for, let's say, triangle. So let's say H is A3. So the typical density is p cube in the graphon sense. So there is no n anymore. And let's say I want to achieve density r cube, where r is bigger than p. So it turns out, roughly, this is the description. So look at the function. So I described that the relative entropy IP of x is a convex function. But now let's say look at the function x going to IP of root x. Now this is not a convex function anymore. In fact, the graph of this function looks something like this. So this is p squared, because IP of p is 0. But it's not convex. But now you can, so now the solution, what the solution of Lubetsky's law is, now you look at its convex minor end. So it's look at the largest convex function, which is below, consider convex minor end, which is the largest convex function, which is below the original function. And the claim is, if R so R cube is the density that I want to achieve. So the claim is if R square comma IPR is actually, so this is a point on the function actually, because IP of R is literally IP of square root of R square. So this is a point on the function, but the point is if this point also lies on the convex minor end, then the answer to this question is R. So if you look at the graphon, which has the smallest entropy with respect to P, but has density at least R cube, then the graphon that minimizes that entropy problem is actually the constant function R, provided this condition is true. Then then the constant function R is the optimal solution. And it turns out that it was also shown that if this is violated, then there is a block graphon construction which does better. So this basically classifies a region of space where the constant function is the optimal solution versus where it's not. And the graph of this region, if you look at the phase diagram, So let's say this is a PR space. So I'm looking at the upper tail problem. So I'm looking at only when R is bigger than P. So it turns out that there is a curve like this, such that this region is the replica symmetric region, which is sort of a physics jargon for saying that the R is the constant, R is the solution. Versus here, where there are better candidates. Is this color actually visible? Maybe not too much. Now, okay, but this is all, it turns out that this R squared to IPR or X to IP root X for a general graph, for a general regular graph, this becomes X to IP of X to the 1 over D, where D is the degree. So for any regular graph, a similar story is true, where you instead consider the function X going to IP of X to the 1 over D, where D is the degree of the graph. But the point is, this sort of argument only works for regular graphs, because like I said, so entropy is a relatively nice function, but the set on which it's maximized or minimized is actually a non-trivial, it's a non-trivial non-convex set. But it turns out that the homomorphism density is something which is also sort of hard to work with. And it turns out that if there is a version of Holder's inequality that actually relates, so the sort of key point is Holder's inequality, sorry. Allows to pass from homomorphism densities to various norms of the graphon. And that actually turns out to be a useful thing. But this sort of argument currently is only sharp for regular graphs, and it's an open problem. To find the exact phase diagram for any connected non-regular graph. So the bound that the Holder's inequality will give will only depend on the max degree. And it turns out that that's not sharp for non-regular graphs. So just want to comment with Bhasha Bhattacharya. We have an unpublished, actually, it's been around for some time, unpublished result, which improves the naive Holder bound for K12. So even for a path of length 2, this problem is getting the exact region is open. Like you look at all so you look at all graphons. So density is p square here. You look at all graphons which has density which is bigger than p square, let's say r square. and you want to look at the one which has the smallest entropy cost, I want to understand the exact region in which the constant function is the solution versus where it's not. And if you apply the standard holder bound from this Lubetzky-Zhao, then the bound that you get for the two path, a region that it's not different from what you get for the triangle, because the holder bound only depends on the max degree, and the max degree of the path of length 2 and the triangle, both of them are 2, and so you don't get any improvement. But you can actually work a little bit more, come up with some better inequalities, and actually get something slightly better, but it's still not sharp. And so this is and any progress for general graphs would be fantastic.
So by slightly better, you mean a slightly larger region?
Yeah.
Where things are, where you have the
so where you have symmetry, yeah. Mm-hmm. Yeah, so the region for the two star looks something like, I mean, like the bound that we have looks I'm not sure what the figure looks like, but in principle, something slightly beyond what is for the triangle.
Is it clear that you always have some non-trivial region where you do not have the symmetry?
So for P very small, I'm like, as you will see, so far we've been talking about P being fixed, and so now we will soon sort of transition to P sparse. So the first comment is for P sparse, where P is going to 0 with n, which actually also kicks in when P is super small. You can really sort of do better by having some block structure and instead of having a constant. So there are some questions here.
And Matas is asking for which graphs.
So one point here. So for no graph, the non-constant maximizer is known. Like it's known that there is something which is better than constant, but for a P fixed, there is no graph for which it's known what the optimal solution is in the region where it's not a constant. Does it answer? Okay. So for P very small, you will see that actually having tiny blocks will actually be more optimal. Okay. Good. Any further questions? Okay, so there are actually simulations. So simulations predict, not literally for this model, but it's actually generally believed that it should be the same for this model as well. But there are related models where simulations are actually done that optimizers in the symmetry breaking region should be stochastic block models with 2 blocks. I think that's what it shows. So the solution should be actually not a constant. When it's not a constant function, it should be like a roughly approximated by a 4-block graphon with different densities across the blocks and inside the block. So that's what, there's been extensive simulations done by Charles Reddin and his group. I don't know. So a lot of things are actually known for sparse graphs where you actually can handle entropy. So for dense graphs, this is roughly the story. Yeah. So this is somehow. Yeah, it's not super clear analytically why it should be, but maybe you can think of doing some perturbative argument to say that, oh, actually, if you have multiple blocks, maybe you can actually improve things by some sort of convexity argument to sort of just go to 2 blocks. Not 4 blocks, 2 blocks, like 4 blocks in the 4 blocks literally, but actually 2 partitions. That's what is expected to.
Can you scroll the tablet? The part you're writing is not visible.
Oh, actually, I see. So did it freeze? I see. Sorry. Oh. Just a sec. Let me try it. Yeah, okay, sorry. Oh, how long has it been not visible? Sorry.
See, when you started writing the simulations predict,
I see, okay.
that was not visible.
Okay, yeah. So, yeah, simulations predict that optimizer should look like this. I say sorry, yeah, so I think it should be fine now. Sorry, thanks, Melinda. Okay. So we'll soon sort of transition into sparse cases where actually you can do a lot because you have a lot more control on the entropy. But one more thing that I wanted to, in the dense case, want to talk about. Yeah. So recall.
Sorry, so for which age are these simulations?
So like triangles, paths of length to like, and also like it's to be completely precise. I think the simulations are not for exactly the setting that I'm talking about. It's about related settings of exponential random graphs, which I'll sort of soon go into, or constraint models, where you sort of look at all graphs uniformly picked from a subset of graphs, which has a given number of edges, given number of triangles, and things like that. Okay, so related to what Omar said, so now we will sort of talk about a particular class of measures. So recall a standard way to prove large deviation bounds is by computing exponential moments. So which actually relates to, so this naturally relates to, so this naturally leads to study of a class of Gibbs measures on graphs of the following form. So probability of G is proportional to exponential of some Hamiltonian, and the Hamiltonian roughly looks like the following. So let's say, so everything has size n, so n squared times, let's say, summation I equal to 1 to s, maybe beta I, t h I g. So let's say you fix graphs h1, h2, hs. So h1 could be an edge, h2 could be a triangle, h3 could be a 4-cycle or whatever. Like, so fix some finite collection of graphs, and now you want to charge a particular graph. The measure should be charging it exponential of roughly something related to the densities of these subgraphs into G. Okay, so which means basically if the beta is a positive and large maybe, then more mass on G with high subgraph densities. Okay, so this is known as the exponential random graph model. Or ERGM. On the other hand, if beta is a negative, then you actually put more mass on graphs that actually, let's say let's say there was only one, which is, let's say, a triangle. So let's say there was just H1 and H1 was a triangle, and beta I was a large negative number. Then you actually put much more mass on graphs that actually have very few triangles. And then you would expect things like, oh, actually then the mass is more or less concentrated on graphs that are mostly like bipartite. So if beta i's are negative, then subgraphs are avoided. Okay, now, so this is not a probability measure. You have to normalize by something to make it a probability measure, and let's call that normalizing constant as z. So z is the normalizing constant, which means that this divided by z is now a probability measure, and let's call psi to be, let's say, the log. So this is also sometimes called the partition function, and so let's call psi to be the log of the partition function. So it turns out, it's not surprising that large deviation theory can be used to study ERGM, and in particular, the free energy or the log partition function. Okay, so what is z? So z is sum over all graphs, exponential of beta, exponential of h. So which is n square summation beta I, the densities. Let's see, what did I write? Yeah, the densities. Now, okay, so I don't remember exactly what I did in the last lecture. So THIG should be thought of as the density of HIG. This is an order 1 quantity. So you basically normalize everything by all the factors of n. So this is supposed to be, so for example, if HI was triangle and G was an Ashwini graph, this would typically be like P cubed, not N cubed P cubed. Another point is you multiply by n squared because that's roughly the entropy of the full system because there are roughly n square edges. So you want to understand that, and it turns out that so you can actually use large deviations to answer this. So psi roughly looks like n squared. Psi is a log of this. N squared times a variational formula. So over all graphons W. Actually, let me just make it normalized. Let me just normalize H. So H is this, and let's normalize. So H is just again an order 1 quantity, so that it makes sense for graphons. So then H of W minus well, I can also normalize this like this, just to make sure that things are normalized. So this is then. So essentially what it says is I want to sum over all graphs exponential of this Hamiltonian. Now the Hamiltonian is literally subgraph densities. So what it does is so if you actually use the large deviation framework of Chatterjee and Varadhan for graphons, so this sum, you can sort of divide your space of graphons into various corners depending on what the value of the Hamiltonian is. So this is a continuous function. So this is the space of graphons. So maybe you partition it. Okay, I'll not continue. But such that in each part, H does not oscillate much. H is a continuous function on the space of graphons. It has subgraph densities. Okay, so now you want to so for Z, you have to sum up the contributions of each of these parts. Now, if this part is close to a particular graphon, then the probability that the 1/2 to the n measure, so z is sort of a tilting of this uniform measure 1/2 to the n measure, maybe 2 to the n square actually, because the system size is n squared. So for each part, the contribution from the exponential h of w and the probability that this 1/2 to the n square mass, if the uniform measure puts here, is roughly comparable to the entropy of w with respect to 1/2. And so, of course, there is a sum involved, but the number of terms in the sum is so small that actually the part that has the biggest contribution dominates. So this is not a very uncommon thing, and this is what sort of comes out of this large deviation theory. This is actually basically similar to an application of Varadhan's lemma given this large deviation. So I won't say much about it. The whole point is, if I have large deviation information, I can use that to understand exponential random graphs. But one thing that happens though is that if beta i's are all positive, so this is proven by Chatterjee and Diaconis in 2013, relying on this previous work of Chatterjee and Varadhan. And in the same paper, it was proven that if beta i's are all positive, then actually nothing very interesting happens. So then the optimizers in the above problem are constants. So it turns out that exponential random graph, if all the beta i's are positive, actually looks like maybe a mixture of Eda-Shreni graphs. Again, the relabeling has entropy, which is exponential in n, or maybe n log n, because there are n vertices. The total possibilities of relabeling is exponential in n log n because it's at most n factorial, whereas all the exponential scales at which we are sort of dealing with here are exponential in n squared. So really, the relabeling actually does not really affect this sort of consideration. But of course, yeah, everything is exchangeable. So any graph, its relabeling will also have the same probability under this measure. Does that answer the question roughly? Yeah. Yeah, so everything is happening at a much sort of larger entropy scale. Okay, so this means basically that ERGM looks maybe a mixture of Eda-Shreni graphs. So not super interesting, but there are interesting questions to be asked nonetheless here. And so this was actually made even more quantitative in a recent work of Eldon and Eldon Gross in, I think, maybe 2018, 19, I don't remember exactly the dates. But, and so there is a, okay, so if beta i's are all positive, then things are roughly like Eda-Shreni graphs, but there could be multiple solutions. And actually, you can ask like, so then there was a sort of paper actually earlier than Chatterjee and Diaconis by Shankar Vamedi, Guy Bressler, and Alan Sly, sorry, which looked at high and low temperature ERGM. So I won't actually make precise what these regimes are, but roughly what it means is in the high temperature, there's a unique solution. This is not literally true, but roughly multiple solutions. Right, so I claim that the optimizers are all constant, but there could be just one unique constant solution, or there could be multiple constant solutions. And they proved that in this case, in the high temperature case, many nice things happen. So fast mixing of Glauber dynamics. Here, slow mixing. Fast mixing meaning order n squared log n. where n is the size of the graph, here exponential in n. But let's look at this regime for the moment. So here it says roughly that there is one Edersheim graph. So there is one P star such that ERGM looks like, okay, so this has to be made, okay, one has to sort of talk about what this means. Looks like an Edersheim graph with density P star, but in what sense? So the Chatterjee diagonist result, or even the Bhamidhi-Bressler slide result, tells you that this is close in cut distance. So close in cut distance. But you can actually ask more. Like, if you actually expect things to be like an Edersheim graph, you can actually ask questions about, let's say, concentration of measure, central limit theorems of observables, like let's say central limit theorem for number of edges in the graph. So of course, in an Edersheim graph, everything is an independent edge. So of course you have a CLT, but if you expect ERGM to be close to an Edersheim graph, you can actually ask things like this. And these are actually mostly open. So in recent work with a student at Berkeley who's now starting a postdoc at UCLA, so with Kyun-Sik Nam. So we showed concentration of measure, actually Gaussian concentration of measure. I'll not make precise statements because I don't have the time. For Lipschitz functions. And this is roughly using Stein's method of exchangeable pairs. And for the second question, we show partial CLT. So what we show is, if you take edges E1, E2, EM, where let's say M is little of n. So maybe one of the sort of the big question is, let's say, to prove central limit theorem for the total number of edges, but let's say you take some smaller number of edges, which is little of n. N is a graph size. And also let's say they are vertex disjoint. So no two edges in this class share a vertex. Then indeed, satisfy a CLT. So whether this edge is present or not, satisfies a CLT as n grows to infinity. So, but it's open to, it's an open problem of, I think, much interest. Prove a full CLT. Is the statement clear? I mean, it was not super precise, but the point is you expect things to be close to an Edersheim, so things should roughly have some decay of correlation. So you should be able to sort of expect some Gaussian fluctuations that we already proved, but to prove actually a central limit theorem is much more delicate. But we can only prove it for a smaller number of edges, and if things are sort of not super, because the point is the correlation estimate that one has actually changes when two edges share a vertex versus when they don't. And so that's why we really need the edges to be vertex disjoint. Okay, so I'm actually
by CLT you just mean for the number of edges in the graph.
Yeah, I'm like you can look at other observables, but the first step is to just sort of look at the number of edges and prove a central limit theorem for that. Yeah, prove a full. Yeah, that I should make that clear. Yeah, thanks. Okay, so that's what I think I wanted to say about sort of the dense settings. I mean, like, there are versions of this even when p goes to 0, and there are structure theorems that actually appear in this work of Eldon and later Eldon and Gross. But let's sort of revert back to our original question of large deviation. So I mean, like, as we have already seen, large deviations and exponential random numbers are not actually that different. Like you can actually, if you have very good understanding of exponential moments, you can actually use that to get some large deviation bounds. But let's sort of just go back to our original setting. So let's go back to this phi h and p delta quantity, which we saw when p was fixed, was constant in some regime and then maybe non-constant in some regime. So now we will consider the case when p goes to 0 with n.
So Frank is asking if a solution is known close to the crossover line in the LZ problem.
For what p fixed? No, I don't think for p fixed anything is known. I think there are some related problems in extremal graph theory. So these are actually not the same problems, but they are of similar flavor. And I think Rasparov actually does have some understanding around some phase boundaries using his theory. But in this concrete setting, I don't think anything is known. But there are related things in extremal graph theory where some progress has been made. Okay, so p will go to 0 with n for the rest of today's lecture and tomorrow's lecture. So first observation, constant function is never the solution. Okay, so what do I mean by that? So I have this optimization problem. I want to look at a weighted graph so that the subgraph density is bigger than typical, and I want to understand what the best possible reweighting is. And the point is, I claim that when p goes to 0, the constant function is actually never the solution. Why is that true? So let's see. So right. So if actually the constant function was a solution, then the constant function actually means that the total, not only does the number of triangles or whatever subgraph you're interested in. Okay, so when I say constant function is never the solution, I mean when the subgraph that you care about is not trivial. I'm like, if the subgraph is literally an edge, then it's nothing different from a coin tossing problem. So let's pretend that it's never, like we're always talking about non-trivial graphs. So whenever the graph is non-trivial, meaning not an edge, the constant function is never the solution, because the cost of making the total number of, so if you actually, the constant function was a solution, then it would actually imply that the total number of edges increase. So in particular, the total number of edges was typically, let's say, roughly n squared by 2, n choose 2, times p, but maybe now that gets boosted up to some 1 plus delta factor. And it turns out this is roughly, the cost is roughly e power minus n squared p with some constant depending on delta. It's sort of an easy check that this is what it will turn out to be. Now it turns out that there are better strategies. Let's say for a triangle, you can actually, so let's say this is my full graph, and let's say I can pick a small part of the space of size np, maybe with some constant, such that I put in all the edges here. So I take an np cross np box, and I put in all the edges there. So how many edges do I put in? That's roughly np choose 2. But okay, so let's ignore the 2 for the moment. So it's roughly n squared p squared. But in a very compact fashion. And so the cost of this is actually what? I'm introducing n square p square many edges. Each of them, the probability of a particular edge appearing is p. So the cost is p raised to the n square p square, which is the same as e power minus n square p square log 1 by p. Now you see that this, so you see that n square p is actually much, much larger than n square p square log 1 by p if p is small. So this is a much more optimal strategy than increasing everything. Okay, so I want to actually, so I'm running out of time, so I want to actually sort of tell you what phi h np delta is. So one has to actually slightly bear with me. So let's say H is a graph, H is connected. And so this turns out to be a strategy to get this boost. Another comparable strategy is actually the following. Take some small part and make everything here one. So you take some small set of vertices. I mean, like, of course, this is so small, you also don't care. Maybe you can make this one as well. So the point is here, you took a small set of vertices and put in every possible edge in that small, within that small set of vertices, which means you planted a clique. So this is a clique. What you're doing here is you take a small set of vertices and you're actually connecting them to everything else and also to themselves maybe. And so this is like planting what we call an anti-clique in our paper, but subsequently has been called the hub. Or it's just basically a very unbalanced, complete bipartite graph. So it turns out that these are the two dominating mechanisms when p goes to 0. So I'll give you the asymptotics for this, but let's say H is connected, and so then I'll define what a of max degree, let's say delta. Okay, and let's say H star is the induced subgraph on degree delta vertices. So if H is regular, then H star is H. But if H is not regular, if you look at the max degree vertices, you can look at H star. H star is sort of the subgraph that you induce on those vertices. And I define IH star X to be the independence polynomial. I'll define what this is of H star, which roughly means the following. This is summation I H star k x to the k summed over k. So I H star k is the number of independent sets of H star of size k. So I have some graph. I have the high degree ones here, the max degree ones here. I look at the subgraph only restricted to that. That I call H star. In H star, I look at the independent set. So independent set, for people who are not familiar, so independent set is a set of vertices with no edges between them. Okay. So I take a graph H, I look at H star, I look at its independence polynomial, and then I look at the solution to this equation. So P H star, oh sorry, I H star. X, so let's call theta to be the solution So delta was the boost that I wanted. So I want to solve this problem. I want to find the best possible reweighting, which makes the H density in my graph to be 1 plus delta times its original density. So I look at this number, theta, and it turns out that this is asymptotic. So phi H n p delta actually roughly looks like n square p to the delta log 1 by p. In the triangle case, delta is 2, so n square p square log 1 by p. And this is going to be two things. So one is, this is exactly theta if it's regular, if H is irregular. And it's the minimum of two things, minimum of theta and 1/2 delta to the 2 over the size of H. Okay, it's a complicated looking thing, but it's not super important. But so basically what it means is the following. So there are two things here, and the solution is the minimum of them. So the two things actually correspond to these two constructions. So the bipartite construction corresponds to theta. If you do it optimally, you will get theta. The clique constructions will give you this. It turns out that if H is not regular, then the clique construction does not make sense. And you only have the bipartite construction, in which case this is what you get. So this is jointly with Bhattacharya, Lubetsky, Zhao in 2016. Okay, so the regime of P must be mentioned. So this is, let's say, for P much bigger than n to the -1 over delta. Delta is the max degree of H. Okay, so this basically says we have these two competing construction, and depending on which one does better, that is exactly what dominates this mechanism. Any questions? So I'm out of time, so I'll continue with this in the next lecture, but I just want to finish with another related setting about, so subgraphs are polynomials of independent bits. So another related setting is arithmetic progression. In random subsets of, let's say, 1 to n, or maybe even z mod n. So essentially what you have is you have some interval 1 to up to n. You pick each entry independently with probability p. So you get some random subset S, which is a subset of 1 to n. And let's say you care about the number of arithmetic progressions. Tk is, let's say, the number of arithmetic progressions of length k in S. And so you can actually develop a similar theory. Instead of the subgraph is nothing very special. These are also polynomials, but it has, instead of sort of tools from graph theory being handy, here you'll have some arithmetic commentaries coming into play, and with Bhattacharya, Fernando Shao, and Yifei Zhao. I forget when, maybe, I don't know. I would like to say maybe, I don't know, 17 maybe, we proved precise asymptotics for the corresponding deviation problem. And it turns out that here actually things like this come out. So related to the following question, given M with subset A of Z, let's say even, of size M, maximizes number of k APs in A. I mean, like, so actually, it's also not unrelated. So in the subgraph problems, actually, things related to this is also relevant. Like, suppose I give you some number, and I want to look at all graphs with this given number of edges. Which is the one actually which maximizes the number of triangles? Here, the corresponding question is: I give you some number, I look at all possible subsets of size m on Z, which is the one that actually maximizes the number of k-term arithmetic progressions in A. So for k equal to 3, this was done earlier by Green and Cisak, and we extended to all k. And the answer is actually not very surprising. So the interval is an extremal set. So unlike the graph case where there were two competing candidates, the hub or the anti-click and the click, in the arithmetic progression case, planting an interval is asymptotically optimal. It's not to say that there are not other, you can see that if an interval is optimal, any dilation of the interval will also be optimal, meaning that you can replace an interval which is an arithmetic progression of actually common difference 1 by any arithmetic progression and of the same size, so that will also work. But those are, of course, of smaller order terms, the number of such choices. But the leading order in the graph case is dominated by clicks and anti-clicks. In the arithmetic progression case, is dominated by intervals. And so I think I'm out of time. I did not sort of talk about how to actually prove large deviation in this case. I only talked about the variational approach of things, variational sort of side of things. And in tomorrow's lecture, I'll sort of start with that, hopefully finish it quickly, and then move to how some of these ideas and maybe new arguments are needed to understand other sort of nonlinear functions of graphs, like edge of the spectrum, the largest and the second largest, and the first few largest eigenvalues. So I think I'll stop here. Yeah.
So let's give everybody the opportunity to unmute their mics, and we'll give a round of applause to Shirshendu.
Yeah, so Shiom is asking about the explicit solution of